samples, and this bunch of sample means will follow a normal distribution with mean mu and variance sigma square over n. All right. Now then, how about the sample variance? So how does the sample variance behave? So we don't know the distribution of s square, but we know that n minus 1 over times s square over sigma square will follow something called a chi-square distribution with n minus 1 degrees of freedom. So we discussed about chi-square distribution, how to look for the CDF and the quantiles. So this basically is how chi-square distributions look like. It's a scale distribution, and it only takes positive values. Positive values. All right. So we also talk about t distribution, which can be considered as a square root, a standard normal divided by w over n. All right. Then this t suppose follow something called t distribution, and with a parameter n minus 1, where z is a standard normal and w is a chi-square with n degrees of freedom. All right. This turned out to be this x bar minus mu s over root n. This one will follow a t distribution with n minus 1 degrees of freedom. All right. So we talk about chi-square distribution. We talk about t distribution. All right. So now today we continue with the last distribution covered in chapter 5, which is to look at the behavior. The behavior of something called F distribution, which is popular because we are interested in looking at the behavior of the ratio of the variances. All right. So this one, suppose follow a F distribution if n1 minus 1 and n2 minus 1. All right. Basically, the idea is that if we have two variables where w is a chi-square n1 and v is a chi-square n2. So we have two independent chi-square random variables, and then we adjust by the degrees of freedom and take the ratio. All right, w divided by the degrees of freedom compared with v divided by the degrees of freedom. That one will follow something called F distribution. And for F distribution, there are two parameters, n1 minus 1 and n2 minus 1. And it turns out that the ratio of the two population variance will follow a F distribution. Not too difficult to prove or to show that. All right? Okay. Now, okay, F distribution. Okay, so this is where we stopped last week. So we are looking at example, and we know that, all right. So we have this light bulbs, and the manufacturer claims that the mu is 500. All right. Now this is his claim. He say that the mu, the average lifetime of the light bulb is 500. So in order to test whether this claim is correct or not, we take a sample of 25. Then check each light bulb's lifetime. All right. And then this. So we decide that, or he decide that. So if you compute this test statistics, and this is a statistics, Why is it a test? Why is it statistics? Because it's a function of the random sample x1, x2 up to xn. X bar is a function of x1 up to xn. S sample, the square root of the sample variance is also a function of x1 up to xn. So the whole thing is a function of x1 x up to xn. So it is a random variable, and these random variables are the random samples. So it's a statistics. So you take a sample, observe all its values, or we call it realization of this random sample. Then, if the value is between these two numbers, then he think that the claim is justified. Why? You can think of it. So basically, it's saying that this quantity is very small because within this minus 2 minus, okay, what is this number? Yeah, 1.711. So it's between minus 1.711 and 1.711. So if you obtain the sample, check it, and then the value falls within minus 1.71 and 1.71, then that means the number is not too extreme. The number is coming from this formula. It basically measures the difference between x bar from the sample and the mu, which we are hypothesizing to be 500. So if this difference are not too big, then that means mu equal to 500 is okay. We don't say we don't against it. We don't do anything to against it. All right. But if the difference is very huge, how big is big? So long as the test statistic compute outside this minus 1.71 and 1.7 interval, then we think it is big, large, and then we will reject the claim. All right? So remember, the idea is that, okay, you get a sample, you calculate it, and the way that we do it is that the chance that fall within these two, all right? So basically we are saying that this T 25 degrees of freedom, and then the chance falls between minus 1.71 and 1.711, all right? This probability, what is the probability that falls within this interval? What's this area? What do you mean by this number and this number? Less than this number. What is the chance for a random variable t? 5%. All right, and this one also 5%. Greater than it is 5%. So therefore, this is 90%. All right. So in other words, if mu is 500, so it's likely 90% chance that it will fall within this statistic will fall within this minus 1.71 and 1.71. All right. So, but if mu is 500, there's still chance that it falls outside this interval, but the chance is only about 10%. All right. So we assume that it is not approximately normal, so that's why this follow a t distribution. All right, so that's why we calculate it, and if mu equal to 518 and the standard deviation, sample standard deviation is 40, and you calculate that it is 2.25. So in other words, what we see here, is this what we observed, 2.25. So is it considered big? Yes, because it falls in the critical region, or the chance that bigger than what we observe is less than 10%. Less than 10%. All right. So, so in this case, we don't believe what the manufacturer claims, mu equal to 500. In fact, based on this data, we believe that mu is bigger than 500. Mu is bigger than 500. How do we know? Because what we see, the sample mean is 518 is on the bigger side of 500. All right? So, of course, based on this one, then the manufacturer may try to claim that it is better. It's different from 500. In fact, it's better. All right, so that's what all this sampling distribution can lead to some decision making or some inference about the population mean mu. All right, how about F distribution? So if U and V are two independent, remember we need this independent random variables. So they behave independently. One follows a chi-square distribution with n1 degrees of freedom, and V has a chi-square distribution with n2 degrees of freedom. All right? Then the ratio U over n1, that means the random variable divided by adjust by its degrees of freedom, compared with another chi-square random variable, adjust by the degrees of freedom, that will follow a F distribution with two parameters, n1 and n2. Now it's important that you have to know distributions and the parameters, and also how the parameters are linked to the mean and to the standard deviation of the distribution. All right? But in this case, for F distributions, the two parameters, one referring to the degrees of freedom of the numerator chi-square distribution, the other one linked to the degrees of freedom of the denominator random variable. All right, so we have this as the PDF. All right, don't bother about this PDF. All right, but you have to remember that F distribution apply to positive x. So if x is negative, the PDF is 0. All right, the PDF is 0. The shape basically is still like this for F distribution. It's still like this. All right. Okay, the expectation of x is n2 over n2 minus 2. All right, and n2 has to be bigger than 2, otherwise it's not defined. Why? Because if n2 is less than 2, it cannot be equal to 2. Equal to 2, this is not defined. So less than 2, this becomes negative. How do you expect your x to be negative? If your range of x is positive, how can the expectation be negative? So this formula is not defined for n less than or equal to 2. So it has to be bigger than 2. And the variance need greater than 4. n2 greater than 4. All right? Okay, here is an example. So we take two random samples of size n1 and n2 from two normal populations with variance sigma 1 square and sigma 2 square. So we know that U follow a chi-square with n1 minus 1 degrees of freedom, while V here, all right, defined like that, follow a chi-square distribution with n2 minus 1 degrees of freedom. And because they are from two random samples, so these two are independent. All right, because they are random samples, two random samples from two different populations, so they must be independent. They cannot be related. All right. So then now I take the ratio chi-square n2 n1 minus 1. This one is chi-square n2 minus 1. Adjust by the degrees of freedom. So then you can see it cancel out. So this follow a chi-square distribution. Oh, so just now I make a mistake. It should be S1 square over sigma 1 square. All right. Over S2 square divided by sigma 2 square. You must take this population variance. But if you assume sigma 1 square equals sigma 2 square, then this will be equal to S1 square over S2 square if sigma 1 square equals sigma 2 square. All right? If they're not equal, then only this follow a F distribution. All right? Why I remember this one? Because it's likely that we are interested in finding out whether the two population variants are the same or not. And application is, remember your two sample, okay, we have, Okay, we will come to that. If we have two samples, we would like to know whether the population variance of these two samples have the same variance. All right. So we would like to find out this, how true this is. So we will base on this. But in general, this is the distribution. This is the quantity that follow F distribution with n1 minus 1 and n2 minus 1 degrees of freedom. This is a very simple but useful properties. So remember, F is U over N, V over M, where U is chi-square N and V is chi-square M, degrees of freedom. Now if I take 1 over F, take the reciprocal, how does it look like? Then it will be V over M and U over N. Right? You just exchange the numerator and the denominator, swap the two. Then what is this distribution? It's a chi-square M, chi-square N. So this will follow an F distribution with M and N distribution. So this, because of the special property about this ratio of the two chi-square random variables adjusted by the degrees of freedom. So you take 1 over F, you just swap the numerator and denominator, so it's still an F distribution, but you have to swap the two degrees of the degrees of freedom. So instead of N and M, so now it becomes M and N. All right? So statistics table, it gives you this one. All right. So by the way, we try, as you can see, the table, statistics table we provide, I uploaded in the IVLE, is give you the upper tail. So this is a constant, such that, all right, this is the number here, such that the chance greater than this number is alpha. And this follows a F distribution with N1, N2 degrees of freedom. Okay, so that is what this constant means. All right. By the way, read the description. Sometimes this number, we represent it by this. All right. So here I write it, the two parameters, N1, N2, followed by the probability that greater than this point. Sometimes we write this probability as a subscript and then use two brackets to specify the parameters. What does this mean? Okay, so this one means an F distribution. Follow N1, N2. So that's the first meaning. The second meaning, sometimes, so you have to read carefully. So sometimes this represents a random variable that follow F distribution with N1, N2 degrees of freedom. Of course, to be more exact or more precise, I should write something like this. Maybe X follow, so then you know that this referring to a distribution, this referring to the random variable. But sometimes when too lazy, we just use F bracket N1, N2 to represent the random variable or represent the distribution. All right? So you have to figure out yourself. But with an alpha, then it's not a random variable. It is a value for which greater than this value, at least in my notation in the notes, greater than this value for a random variable follow F distribution, that greater than this value with probability alpha. All right? So, so this is what it means. All right? So, this means that a value 6.26 for which an F distribution, F, here is the random variable, follow F distribution with 5 and 4 degrees of freedom. So this is F distribution with 5 and 4 degrees of freedom, and this is 6.26. and the chance greater than it is 5%. So that's what it means. All right? Then these are the Excel command, f.dst, to give you the CDF. All right? Unfortunately, they use a different notation. So they talk about the cumulative CDF from the lower end. So it's the lower end probability. All right? So they're referring to F distribution with N1, N2 degrees of freedom. This value, okay, this will give you, this is the F, this will give you, this whole thing will give you this probability. Give this probability less than F. F is a value. I use lowercase. So this is a particular value. Here, I want to know what is the chance less than this value. And the probability is given by this statement. All right? While inverse is the opposite. So you're given the P, this is P. So I try to figure out what is this C, such that the probability less than this C is equal to P. All right? So this will give you the C, or the P, we call it the P quantile. Okay? All right, so we have, so you can see we have this property. All right? So think of it. Think of it. So we are saying that this is a number. What this number means is that this follows a F distribution with N1, N2 degrees of freedom, and this is the value. All right? This is the value. Let me call this A. This A. This is A. So the chance of greater than this value is, let's say, 1 minus alpha. All right? Then, in other words, the probability of a W greater than A is equal to 1 minus alpha. Then now, if I take the reciprocal of it, if I put this 1 minus alpha, then what is this inequality? Same or reverse? These probabilities are the same. That means this is equivalent to this. If I put equal, would they be the same? 3 bigger than 2, right? Take the reciprocal. Which one is bigger? All right? So it's like that. All right? But according to my notation, 1 over W greater than 1 over A. All right? Now, instead of less than, I talk about bigger than. So it's 1 minus alpha. So it's equal to alpha. All right? Okay? So, in other words, A, 1 over A is equal to F alpha, right? But now the 1 over W is a distribution of N2, N1 degrees of freedom. I have to swap the degrees of freedom, and greater than it is alpha, so it's alpha. So that explains. So this is 1 over A, right? So 1 over A is a value, F distribution with a degrees of freedom swap, which is N2, N1. Greater than this number is alpha. So it represents by this. Okay. why bother? If you have a powerful calculator, a powerful computer, just a computer, not only powerful, you don't need to know this fact. All right? But for statistics table, sometimes they only give you maybe 0.75, give you the value. So that greater than this number is 0.25, greater than this number is 0.10, and so on. But did not give you any values on this side. All right? So you still have to work it out. How? We consider a distribution which swap the degrees of freedom. All right? By using this fact. All right. So this point, I call it A, is the same as 1 over A, but now, all right, so this is alpha. But consider the distribution N1, instead of N1, N2, is N2, N1. That's what I'm trying to say. All right. So this is just a properties, a straightforward properties by consider F. If you consider 1 over F, you have to swap the numerator and denominator. So now your distribution change, and also you establish this identity. All right. So you can see that from here, this number is 3.33 is a value under 510 degrees of freedom. It is greater than 3.33 is 5%. So now I want a number from a distribution F with degrees of freedom 10 and 5. Swap these two numbers. So greater than this number is 95% chance. What is this number? So this number is equal to 1 over 3.33. So it's 0.30. All right. So in other words, if this is F510, then this value 3.33 bigger than it is 5%. Okay, so that's what we have. Now, if I swap it and consider F10.5 distribution, so take the reciprocal of this one. So this is 0.30. So greater than this number now is 95%. 95%. All right? Okay. Example 2. We have two samples with different sample size, and suppose they're taken from a populations with variance sigma 1 square equal 10, sigma 2 square equal 15. So we ask, find the probability of the ratio of these two sample variance greater than 1.26. So in order to find this probability, we need to know the distribution. What's the distribution? The distribution is a F distribution with a degrees of freedom, not 25 and 31, but instead it's 24 and 30. N1 minus 1 and N2 minus 1. Why not 25, not 31? Because it's not S1 square follow a chi-square. It is N1 minus 1 S square over sigma 1 square. Follow a chi-square with a degrees of freedom N1 minus 1. That's why I have to subtract 1. All right? Okay, so the rest will be quite straightforward. So I want to calculate this probability. I divide by 10 for the numerator and 15 of the numerator. So I have to do the same thing on this side, which means that I divide by 10 and multiply by 15. Otherwise, the inequality is not the same. I mean, the event is not the same. Why I have to do that? Because I don't know the distribution of this one. The distribution that I know is S1 square over sigma 1 square, S2 square over sigma 2 square. We know the distribution of this one. Not the distribution. This distribution, we don't know. This distribution we know, provided that you know what sigma 1 square and sigma 2 squares are. So sigma 1 square and sigma 2 square. So that's why it's divided by 10 and divide. This is sigma 1 square. This is sigma 2 square. All right. So this follows F with degrees of freedom n1 minus 1 and n2 minus 1. All right. So the probability is 5%. All right. Where F follow a distribution, F distribution with degrees of freedom 24 and 30. All right. So we finally finish this chapter 5. Chapter 6. Okay, before we start this, just let you know what we are going to do for this chapter. Estimation is a very big problem. It's just a guess. You can guess whatever you like, use whatever method you want, all right? But here we try to use a statistic methods, try to draw some guess that should be reasonable. So the problem that we are considering is very simple. Basically, it's concerning about mu and sigma, the population mean and the population variance. So it can be just one population. So in that case, we're considering how to guess or estimate mu or estimate sigma square. We also extend it to two populations. So we are looking at the difference of two population means, mu1 minus mu2, or the ratio of the two variances, sigma 1 square over sigma 2 square. And there are one more complications that we would like to find out. Instead of looking at two population means, we are looking at the related samples. That means they are not independent samples, but they are from a related samples, like before measurements and after measurements. So we are still looking at a sort of difference in means, but it's not mu1 minus mu2, but instead it is the difference, which is maybe xi minus yi. So we look at the mean of these differences, whether it's equal to 0 or not. So that is a related sample. So these are things that we'll like to investigate. All right, point estimation, parameter and statistics, unbiased estimator, interval estimation, confidence interval. Now, you may come across all this, maybe at least for one population case. So you have a formula, all right, but you have to know more about just the formula. At least understand the rationale that based on which you derive your formula for like estimators, like confidence interval, and things like that. All right. Okay, so confidence interval for the mean and sample size, confidence interval for the difference between two means, and finally confidence interval for variances. For variance, no S, and the ratio of variances. So in other words, we try to look at mu1 minus mu2, sigma square, and sigma 1 square over sigma 2 square. These are the few things that we are going to discuss in this chapter. In fact, one more thing that we should look at, maybe mu d, where d is the difference between these are the before, these are after, or some related pairs observations. And there's something that may be new to you, how to get the sample size. All right, so we'll discuss this. Okay, so now what we need, well, how to formulate the problem. So we are looking at, all right, some characteristics of the population, so which we represent it by, because it's a population, so can have many different values. So this characteristic is considered represented by a random variable x. All right, and this x I repeat again and again. So we want to know how this random variable behaves. So it's described by the probability function or probability density function, f of x. All right? And this function usually will involve x and also involves some constants. And this constant is to characterize the distribution. All right? So for example, we say that x follow normal mu sigma square. So normal distribution has a form, but then within this formula, there are mu and sigma square inside this formula. Very complicated. 1 over square root 2 pi sigma exponential minus x. You don't have to copy that, right? So you can see that this is the formula for the density function. It involves x, we involve mu, involve sigma square. And different mu and sigma square will give you different normal distribution. That is about the population or how x behaves. All right? So there are two parts here for the distribution. One is the form of the distribution, the form of the PDF. So this is the form. But within this expression, you can choose your values for mu and for sigma square. That means choose the value for your, we call it parameters. Different values of the parameters will give you different distribution. Although it's still considered as a normal distribution, but there are different normal distributions with different values of mu and different value of sigma square. All right, so the form is determined by the density function or probability function. That means determined by this f of x. And within, there's also a parameter, all right? So we assume that this form is known. That means we know this form, but we don't know. Sometimes we don't know mu, sometimes we don't know sigma square, and sometimes we don't know both of them. So this unknown constants in the f of x is called unknown parameters. Parameter is just some constants about this PDF or PF, probability function or probability density function. We need to know that to identify the distribution. And the problem is that we don't know, okay, we know the form of the distribution, but we don't know exactly what distribution it is. All right? So we would like to find out what these parameters are. All right? I make it simple, I write theta here. Theta can be more than 1, or it can be a vector. That means it can be theta 1, theta 2. Just like normal distribution, you have mu and sigma square. All right? Okay, so how to get the idea of this unknown parameter theta? So we take a sample, a random sample. So a random sample, before you measure it or take the observations, realize it, is represented by a set of random variables, x1 up to xn. But once you do the experiment, like toss a coin, before you toss, it can be head or tail. But once you toss it, then you have the outcome. The outcome is head or tail. So here the lowercase x1, x2 up to xn represent the outcome of you get the sample and then you measure it or you observe it and you get the numbers. So the x1, the lowercase x1 up to xn represent the realization of the random variables. All right? So we observed these numbers. All right. So we will try to estimate this unknown parameter theta based on what we observed. Or you can term it as based on a statistics. All right? We try to estimate this theta based on the statistic. That means a function of x1 up to xn. For example, a function can be x bar. That means 1 over n sum of xi. So that's a function. So I can use this function to estimate an unknown parameter. Whether this is correct or not, or whether this is a good estimator, we have to study. But this is an example. All right? So I use a function of the random variable. Then now I go and really collect the sample and measure it or take the observed value. Then That means I know the values. And substitute in this formula, that means take the average of all the values. Then I got a realization of X bar. Then I use it to estimate theta. All right? So there are two parts. One is an estimator, which is based as a formula on the random sample x1 to xn. That will use to estimate the unknown parameters. Then if you take a sample, usually that's the part that you calculate. Take a sample, now I got all these sample values, and then I calculate based on that formula of the statistics, I calculate the value, and then I use that particular value to estimate my theta. All right? So here, there are two ways to estimate. The one that I just mentioned is called point estimate. All right? So let me just, if I interest in the population mean, so I use this, all right, to estimate mu. So this is a random sample, a random variable. So you take a sample, you have a different value of X bar and so on. Now, how good is this estimate? I would say that it's always wrong. You will never get the correct mu. All right? Why? Mu is a constant. You take a sample, calculate X bar. The chance that X bar equal to mu is almost zero probability. But based on what we discussed in the last chapter, whether I still remember this law of large numbers. So if I get a huge sample with huge sample size, I hope you distinguish that. I'm saying that I get a sample big enough, no, not enough, but big. Then my X bar should be very close to mu. But let's say if I just take 100, then the X bar that you compute may be very different from the mu, or maybe not, but still not exactly equal to mu. So that's the point that I want to bring up. All right. So your estimator or the estimate will not be exactly equal to mu. So X bar can never equal to mu. All right. What I'm saying is that this one is a random variable. How can a random variable equal to mu? Wrong. After you take a sample, you have the observed value. So this one also cannot equal to mu. All right? It's wrong. All right. Hey, since it's wrong, why I still use this X bar to estimate mu? Yes, we know that it's not exactly, but that's the guess that I can provide based on what I observed. All right? Okay, what's interval estimate? So you think, give you a point estimate, all right? It's never be the actual one. I mean, cannot be the correct answer. So how about give me an interval? Saying that, okay, I give you an interval, provide you an interval, so that this interval will cover the true mean, right? So this time should be better, right? So instead of one number, I give you an interval. Of course, the best interval is from minus infinity to infinity. No matter what your theta is, I always cover you. I always correct. So like if I ask you, all right, what is the average temperature throughout one day? All right. Or in Singapore, what is the average, let's say in October, what's the average temperature? All right. So, or not average, maximum temperature. So that is a constant. Or for example, the maximum temperature for last October. All right. Throughout the 31 days in October in 2018. So that's a number. All right. So of course, if you check, you can get this one. But suppose I don't know. Okay. I don't have the record. I only have records this year, this October. All right. Let's say I have all the 30. Today is what? 29th. I don't have today's maximum. I have not finished yet, so I don't have the maximum. So I have 28. So what to do? I have 28 maximums maximum for 28 days. Each day I have a maximum. Then how to estimate it? So based on this one, I may just come up with a number. All right. But the idea is that, okay, based this one, maybe I say that, okay, the maximum temperature, not from minus infinity to infinity, maybe between 0 to 100 degrees Celsius. It's almost correct in Singapore. Maybe in most part that below the, it's not North Pole, not South Pole, then maybe it's, no, not so North, not so South. All right. But 100 is still a big number. How about 0 to 40? In Singapore, may still okay. All right, but we don't want to have such big interval. I want to cut it into a shorter interval so I can use it. So what happens if I say it's from 24 to 32? The maximum temperature is from 24 to 32. So it's quite short interval. In fact, this is also quite, 32 maybe not. Change it to 34. From 24 to 34. So it's almost cover the maximum temperature of October. So my point is, I tried, instead of using 1, I try to get an interval. All right? So that I will cover this true unknown parameter with a very high confidence or a very high chance. All right? So, so that's the interval estimation. So we'll cover that. All right? So upon estimation is a function of the random variable. All these Greek letters, mathematicians like, especially probabilists or statisticians like to use Greek letters. So you have to understand the Greek letter. So the bracket, inside the bracket is x1 up to xn. That means a function involves x1 up to xn. These are random variables. Represent the random sample. This capital letter theta, all right? So this just represents a function. This is a function, all right? Represent a function, and so this is a statistics. Why? Because it's a function of the random variables, the random sample. So it's a statistics, and then we call this whole thing a theta hat. All right. So this is a point estimate because it gives you only one value if you have the sample. So all this related to theta. All right. So this is called a point estimator. Example is x bar to estimate mu. So this is a point estimator for this one. And what is this? This one we call it estimate. So estimator is the formula. Estimate is once you get the sample, you get the realizer, you observe the sample, you substitute the values in your estimator, then you got a realization of the estimator. And we call that an estimate, right? So statistic is the function of the random sample, does not depend on any unknown parameters. And this is very important. Does not depend on any unknown parameter. So this is a statistics because this is 1 over n summation xi. All right? So once you got the random sample, you observe it, you can calculate your x bar. So I think I give you an example, right? Now, this one is also a statistics because once you get the sample, you observe it, you can find out the maximum. And that one does not depend on any other knowledge. So long as you observe your random sample, you will get it. So they are considered as statistics. So what is not a statistics? This one. In order to compute this one, so I take a sample. So I observe x1 up to xn. But can we compute W? Cannot. Unless you know what mu is. What mu is. All right. So if mu is known, then this is considered a statistics. But if mu is unknown, then this is not a statistics. All right. Remember, the only thing that you can vary is the random set. That means you can have x1 up to xn there. No matter how you have the function of x1, xn. But you cannot involve anything that is not known to you. If once you involve something like that, then that is not statistics. And it cannot be used as an estimator. All right? So this is not. All right. So how to estimate mu? So we use the statistic x bar. All right. And the value of x bar, this value of x bar means that it's a realization or observed value. How to observe? You take the sample, really observe the value of each one in the sample. So that is what I call observed. All right, you observe x1, observe x2. So all this. So in other words, you have this. It represents a random sample. You really take a sample and then observe it, then you see this. All right. So you take the average of all this. That will give you the little x bar. That is the observed value of the random variable capital X bar. All right? So that one, x bar, little x bar, is considered as estimate for mu. Capital X bar is a random variable, it's an estimator for mu. There's a formula for you to compute the estimate. All right? Formula, when I say maybe it's not accurate. It's a statistic that for you to compute the estimator or calculate the estimate of the mu. So here's if a sample mean of random sample, all right, taken from a population with mean mu is 5, then the point estimate for mu is 5. So mu, constant. Mu. I forgot how to write the capital letter for mu. Okay, I try to distinguish between estimator and estimate. So I use capital letter to represent the estimator, which is a function of the random sample, capital X1 up to Xn. But I forgot how to write mu. I know theta, then this is the capital letter, but mu. Okay, anyway, so assume if this is the capital letter, then this represents the estimator. All right. Then if it's lowercase, then it represents the estimate. So in this case, we already observe and get the x bar, the little x bar, equal to 5. All right. Remember, this 5 comes from one particular sample, and the sample average of that particular sample is 5. So now we have this number 5 to estimate, to guess what mu is. So we guess that mu equal to 5. All right. So remember, different random sample gives you different point estimate for mu. All right. But the estimator will remain the same, right? Because it's just a formula. It's just average of capital X1 plus capital X2 up to capital Xn. All right. The change is only when you take the sample, you try to observe it. So now the random variable X1 take a particular value, because now you look at your sample and observe what is the first value, what is the second value, and so on. Interval estimate. Okay, so here's a little bit complicated. I want to find an interval. So to many of us think interval, I'll just give you a -1 to 1 is an interval, or 0 to 5 is an interval. All right, but now we try to define, follow from the idea of estimator. I define two things. Both are random variables. All right, both are random variables. Both are random variables. Random variables, I remember, is a random variable. And then the interval, capital letter. This It's an interval. How do we know it's interval? I make sure that this random variable is always less or equal to the other random variable. All right? So this is a random interval, huh? Just like the random variable. But here, it is more than a random variable. It is an interval of the two endpoints. Each endpoints are a random variables. Each endpoint is a random variable. So this is a random interval. All right? So this one, we say that, all right, this, all right, is a random interval that contains the parameter theta with a high probability, with a certain probability. All right, so for example, we look at sigma square. Right? In this case, sigma square is the unknown parameter. I try to find a random interval that covers sigma square. Sorry, not sigma square. Sigma square is no. I want to try to get cover mu. Cover mu. Sorry, sigma square is no. I want to estimate sigma. I want to estimate mu, the population mean. Assume sigma is known. Sigma is known. Why I have to assume sigma is known? Because otherwise I cannot compute this one. All right? I need to know that sigma is known. So I define this random variable called theta L hat, which is defined as x bar minus 2 times sigma over root n. Is this a random variable? Yes. Why? This is a random variable. Is this a random variable? Sigma is known. Although I don't know, let me repeat again. Unknown constant is not random variable. Constant that unknown is still a constant. You just don't know where it is. Random variable can take many values with different probabilities or previous probability density. All right? So you have to distinguish between random variable, which we know that, suppose we know that it is over a certain range of values. It takes more than one values. And not just the values, but also each value suppose associated with a quantity which is either a probability or a probability density. All right, so that's a random variable. While unknown constant, okay, parameter is an unknown constant. It's a constant, it's fixed. Although we don't know where it is, but it is fixed. It won't change. It's a particular value. All right, unknown constant. Although I don't know where is it, but still one value. While random variable must have more than one value. And not only that, also associated with it probability or probability density associated with each value. Okay, so this is a constant. This is a random variable. So theta L hat is still a random variable. So similarly, this is also a random variable. So is theta L hat less than theta U hat? Huh? Is this correct? Sigma, is it positive? Sigma over root n, is it positive? 2 times sigma over root n, is it positive? Yes. So x bar, no matter what x bar, this x bar is the same as this x bar. They are the same thing. Huh? So one is x bar plus a constant, positive constant. Of course, this value will be bigger. The other one is x bar minus the same constant. Of course, it's smaller. Right? So this is always true. All right? So then we can specify that this random interval, all right, as an interval estimate of the mu. All right? You may wonder why such interval? It's very simple. If you want to say anything about mu, what is the natural choice from the data? If I want to say anything about mu, the population mean, I have a sample, x1 up to xn. All right? So Does x1 tell you anything about mu? Yes. x1 comes from normal with mean mu, right? What is the expectation of x1? Mu, no? What is the expectation of x2? Also mu, right? But how about if I take average of all this? The expectation is also mu, right? So what I'm trying to say is that there's many ways to estimate these parameters. So here I use x bar, all right? So I use x bar. So I use this one, this as an interval. So I would like to know what is the chance that mu falls, let me call it theta L hat and theta U hat. What is the chance that this random interval will cover the mean mu? All right, we would like. Do you think you can work out this probability? Yeah. Usually, we have working in a problem like with the random variable in the middle, x or x bar greater than a, less than b. What is that probability? We can work it out. But now, it is the x bar minus something as one end of the inequality. Then in the middle is mu. Mu is a constant, remember. And then the other end is mu, x bar plus some constant. Right? Do you know how to calculate this probability? Huh? To calculate the probability, you ask yourself, what is the distribution of x bar? Do we know the distribution of x bar? Okay, even if we don't know the underlying distribution, okay, the first simple one is that, okay, the population is normal, so x1 up to xn are normal, and then you know the distribution of x bar, which is normal again, even if you don't know the underlying distribution. So what is the approximate distribution of x bar? By central limit theorem, provided that your sample size is big, then this is approximately normal. You just have to figure out what is the mean, what is the variance. All right? So I presume everyone knows how to compute probability of x bar less than, greater than a and less than b. Then now go back to this one, how to compute probability of mu. This is theta hat L, right? So how to compute this probability? I don't know how to compute it. But compare with this one, can I just, remember, inside the probability statement, there are two inequalities. The lower, this the one that, one inequality is x bar greater than a. And at the same time, x bar is less than b. So there's two inequalities there. We also have two inequalities here, right? Two inequalities here. One is mu greater than x bar minus 2 sigma over root n. All right? One is mu greater than x bar minus 2 sigma over root n. That's one inequality. Can I rearrange this inequality so that x bar is on one side? How? How can get x bar on one side? Throw away, not throw away, move, whatever, extra to the other side. All right? For inequalities, you have to pay attention. Adding a number will not reverse the direction of the inequality. But multiply or divide by something, you make sure that whether it's positive or negative. If it's negative, then you have to reverse the direction of the inequality. So this one, you can write it as x bar less than mu plus 2 sigma over root n. All right? So similarly, you can get from the second inequality, which is mu less than x bar plus 2 sigma over root n. So the other one, mu less than x bar plus 2 over sigma over root n, now becomes x bar greater than mu minus 2 sigma over root n. It's just like magic. I just swap the mu and sigma. But no, don't do it like that. I really have to try it out. I work on the two inequalities. All right? The first appear as mu on one side of the inequality. I try to do something so that it's x bar. X bar is the only term on the end of, or on one side of the inequality. It can be on the bigger side or on the less side. All right? So rearrange it so it's such. Now the two inequalities becomes like that. So my confidence interval is x bar lies between this number and this number. All right. And I work out the probability. So instead of work out this probability, I just work out the probability of x bar less than this one and x bar greater than this number. So that one, we should be able to do it. All right? So that is an interval estimator. I will come back talk about this probability again. All right, so now we would like to know, okay, just estimator, point estimator. So what are the properties about estimators? So one nice property is unbiased estimator. All right, an estimator is an unbiased estimator for this unknown parameter if expectation of this estimator is equal to theta. All right, what it means is that you use this formula. When I get a sample, I do the realization. I got the observed value of this estimator. All right. Take another sample, get another observed value. A third sample, get another value for this estimator. Then I have all this. I take the average of all this. I should expect it's equal if you have large number or infinite number of samples. Then this number we expect it to be the same as the theta. So that is called unbiased. So obviously, an example is x bar. Expectation of x bar is equal to mu. So x bar is an unbiased estimator for mu. X1. Is X1 an estimator? Is it a function of the random variable? Random sample? Yes. That means you got X1 up to Xn. I just don't use the X2 up to Xn, I just use X1. All right? So it's a function of X1 up to Xn. When you say a function, you don't have to include everyone, x1 up to xn, in your function. I can drop some of them. Here, I just drop everyone except x1. So x1 is a function of the random sample. It's a statistics. I can use it to estimate mu. Can I? In fact, what I want to ask is whether this is an unbiased estimator. Is it an unbiased estimator? X1 is just one of the population value. Is it unbiased? Don't say yes or no, you have to answer why, right? So why is it unbiased or why is it biased? So you have to check this one. What is expectation of X1? Don't tell me that you don't know. Huh? It's equal to mu. Huh? Right? So X1 is unbiased estimator for mu. So now, make it more complicated. So I have X1 as an unbiased estimator. X bar, average of X1 up to Xn, is also an unbiased estimator. Both are unbiased estimator. Which one should I use? No difference. I like x1, so simple, just one number. I like x bar, so many of them, I take the average. Which one should I use? Or it doesn't matter. So what do you think? So, guess, of course. I never heard of using x1 as an estimator for mu. If I have a random sample, I always take the average. So average must be the answer. But you must explain why. In fact, we can easily find out a reason. What is the variance of x1? Sigma square. Right? What is the variance of x bar? In fact, we cover in chapter 5. What is variance of x bar? Is it sigma square? What is it? Sigma square over n. Right? Is it bigger? Which one is bigger? Variance of x1 or variance of x bar? Which one is bigger? Variance of x1 is sigma square. The other one is sigma square divided by n. N is, if it's 2, then it's already half the variance of x bar, x1. So of course x bar is better. That's why we use x bar, not x1. All right? In fact, we want to have bigger sample. All right? So unbiasedness. So here, this is also can be shown, all right? But we can work it out, but it's not that the easiest way to work it out, although it's to express this as summation xi square minus nx bar square. Then expectation of xi square. This one equal to what? What is expectation of x square? It's equal to sigma square plus mu square. That is the variance of xi plus the square of the expectation, right? Sigma square, mu square. Because variance of x equal to this minus this. So that's, all right? So you can work it out. To show that expectation of s square equal to sigma square. So it's unbiased. So then, if I define is this unbiased? So, follow from the definition, ask yourself, is this correct? Obviously not correct. How can this one give you expectation equal sigma square? This also gives you expectation equal sigma square. These two are not the same then. How is s square and w related? You multiply w or s square by n minus 1, right? Then you got this part. That means this part. Then divide it by n. Then this is your w. W and s square are not the same. They're w equal to n minus 1 over n times s square. So if expectation of s square equals sigma square, then expectation of w cannot be sigma square. In fact, expectation of w equal to n minus 1 over n times sigma square. So it's not an unbiased estimator. All right? I think it's on the next page. Oh, you see? Divide by n. This is t. Divide by n instead of n minus 1. Then expectation of t is n minus 1 over n sigma square, which is not sigma square. So it is a biased estimator for sigma square. Now, but what happens if n is very, very, very large? Then what can you say about n minus 1 over n? It's close to 1. It's not exactly 1, all right, but close to 1. Asymptotically, it's equal to 1. That means if n equal to 1 million, not big enough. N equal 1 billion, not big enough. But if n is big, goes to infinity, then this n minus 1 over n is approaching 1. So in that case, this t is considered as an unbiased estimator when n is very, very, very big. So this one, we say that we have a name for it. It's called consistent estimator. So that means only when n is very huge, then it looks like as if it is an unbiased estimator. But while sample variance, S squared, is an unbiased estimator, it doesn't depend on your sample size. The expectation of S squared is always equal to sigma squared. And in fact, even we don't have to assume normal distribution, this is always true, provided that sigma squared exists. All right? So in fact, although I did not write it down, to compare different estimators for the same parameter, we look at unbiasedness, whether the expectation of the estimator equal to the parameter. So in this example, expectation of t does not equal to sigma squared. So t is a biased estimator of sigma squared. So in that sense, it's not good. Compare with S squared, because S squared is unbiased. Another thing that I mentioned earlier is that the variance. We want to have a smaller variance. But if it's biased, even you have small variance, it's no good. I think I give this, let me give you this picture. Throwing tartar. So there are many, right? So this is the pond. I want to hit this using my tart. So let me draw all the circles. So this is my answer. I use tarts to hit it. All right? I'm a very skillful tart player. I always hit. Very precise, very close. Each time I land in the same place. Is it good or not? Very precise. The variation is very small. But the bias is very big. Because what I expect is not the same as what I'm supposed to hit. So the bias is big. So it's not good. All right? Okay. So how about this guy? All right? This is the pawn, the bull eye. So I hit. Oh, very bad. But the average is very close to here. So it's an unbiased estimate. All right? That means you take when I throw a tartar sled, I take a sample, and then I take the realization, I got 1 point. Hit it, see how far it is. Yeah, it's variation is very big. But then the average is the same as the target. So in that case, it's also no good, right? So our estimator is considered good, provided that the bias is small. That means it's not too far away from your parameter, and also the variation is also not very big. So that one is called mean square error. This is the estimator. This is the parameter. You square it and find this one. This is called mean square error. I don't know what's the difference. All right? You can think of it like this. T, using the T here, minus sigma squared. All right? This is the answer, the parameter I want to estimate. This is the estimated T. So I look at the estimator, compare with the parameter, square the difference, take the expectation. That is called mean square error. So follow the same argument, the estimator as S squared, the sample variance, S squared, minus the parameter. Look at the difference, square it, and then take the expectation. So that's the mean square error. But do you know that this last expression also have a name for it? Do you know what is it? Can you see that? This is the square of the difference between a random variable and its expectation. What do you call this one? The random variable minus its expectation, square the difference. What do we call that? Variance of x. And this is not the variance of t, y. This is not the variance of t. This is the variance of s squared. This is not the variance of t. Why? In order to be variance, what is this? Expectation of the random variable. Is this the expectation of s squared? Yes, we can show that. Is this the expectation of t? No. Expectation of t is equal to this one. So that is not the expectation of t. So therefore, this is not the formula for the variance. In fact, this formula consists of two parts. It's the variance as well as the square of the bias. All right. All right, so interval, okay. So these are extra things. I just want you to know that when you have two unbiased estimator, if you want to compare, so that is another quantity that you will look at, the variance. But how to combine the bias and the variance? So this is a wonderful tool called mean square error. You will hear this a lot when you try to study the properties of estimators or use the mean square error or different statistical methods. And the definition is the expectation of the random variable minus the true answer, the parameter that you want to estimate. If it's unbiased, then this formula is the same as variance. All right. Otherwise, there are two different formulas. All right, interval estimation. I'm sorry, I have to too slow going. Okay, so this is the interval estimate. Two random variable. So that is a random interval cover theta. So the value of the statistic for a particular sample and then the sampling distribution of theta. So we need to know the sampling distribution of this estimate theta hat in order to compute this theta L hat and theta U hat. All right, so here's the idea. So this is the point estimate theta hat. All right, you take a sample or you have this formula to compute this estimate. All right, then this is the upper confidence limit and this is the lower confidence limit. All right, and this is the width of the confidence interval. So the idea is that we try to get this width as small as possible, but still have the same chance of covering the true parameter. The way that we do things is still have similar chance of covering the same unknown parameter. Just like I say, if I say that, okay, tomorrow's temperature is between 0 and 100 degrees Celsius, big interval, and sure I will cover the true, the temperature, the maximum temperature tomorrow. But then if I say, oh, it's between 29 and 32 degrees of Celsius, a very small interval, but then the chance of covering the maximum may be very small. So different samples, you evaluate different estimate and hence different theta log, the lower limit and the upper limit. So therefore, this is considered as a confidence. This is considered as a random variables. This is a random interval. All right. So here I try to explain is that, okay, you take a sample, based on the formula, you calculate a particular value. This depends on the distribution of theta hat. All right. Take another sample, you calculate this. Remember just now I have this formula, right? X bar minus 2 sigma over root n and x bar plus 2 sigma over root n. So I take a sample, I calculate x bar, and then I can calculate these two values, so we form an interval. I take another sample, I have x bar, I calculate another interval. So I can have many, many intervals. So in other words, I have many of these values. So I can consider this as a random variable. I represent it by theta L hat. All right? Or I just use this formula. Consider this as the random variable x bar. This is the random variable x bar. Then this is the random variable. And this is also a random variable. Upper or u. Okay. So this interval may contain or may not contain the true parameter theta. So what we're trying to do, here's the rationale or the foundation for confidence, to look for a random interval, which means that these two are random variables, all right, such that the probability of this random interval cover the true parameters is equal to 1 minus alpha. All right? Remember what I said? Although here we have two inequalities, each one with theta on one side, only theta on one side. You can rearrange it in terms of the random variable involved, all right? And then becomes something like probability of the random variable theta between two constants, A and B. All right. So to get this probability, so that is equal to 1 minus alpha. So now this will give us this 1 minus alpha. We have a name for it. We call the confidence coefficient or confidence level. Confidence level. So the bigger the confidence level, the more confidence that we have. So that's why you heard about 95% confidence interval or 99% confidence interval. So in other words, the way that we construct the confidence interval has very high chance to cover the true parameter. It's the way that we construct. But once you take a sample and then you observe all the values and compute an interval, you realize the random interval into an interval. So that interval is either cover or do not cover, or does not cover the unknown parameters. All right, so here, so this is going to show you how. All right, now this is the unknown mean. So suppose we know that it's fixed there. So we draw a sample, calculate x bar, so I call it x1 bar. That's the sample mean for the first sample. Based on the formula, theta, this theta log and theta u, all right. So in the example that I gave earlier, it's something like this. 2 sigma over root n, for example, and then x bar plus 2 sigma over root n. We can modify it, but this is just an example to illustrate. Based on this formula, here, I give you, this is, instead of 2, I use z alpha for 2. So I construct, based on a sample, I construct an interval. That is a realization of the random interval. We take sample, observe it, calculate the interval. And this interval happens to cover the true answer. Cover the true answer. I take another sample, x2, x bar here, and construct the interval. All right? Take another sample and more samples. So out of so many samples, each time I construct the interval, I got a realization of the confidence interval. And out of so many confidence intervals, or realization of the confidence interval, about 1 minus alpha, about alpha of them will not cover the true parameters, such like this one. All right. And 1 minus alpha percent, or 1 minus alpha of them will cover the parameter. So that's what we interpret, how we interpret the confidence interval or confidence level. All right? So a particular interval will either cover or does not cover. But what we're trying to say is that the random interval that we construct, the formula that we construct, if you repeat it many times, out of so many times, about 95% will cover if it is 95% confidence interval. All right? Okay, I think I need to stop here, and we'll continue this Thursday. So we'll I will go a little bit faster next time, but basically I already explained the basic idea of this estimation. All right, so we just apply the formula, how to get the formula. All right.